in about 30-45 minutes from now. So I want to make sure that I point that out to be sure to look at the handouts for this session and to download the NFPA 54 table document.
All right, Larry, I got 12 o'clock here, so we'll get going. Good afternoon, everyone, and thank you for joining us today for Jeremias University. My name is Dean Lees, and I'm on the engineering and marketing team here at Buckley. The course you'll see this afternoon is boiler and appliance vent sizing and theory. This is part one of a three-part series that Buckley and Jeremias are hosting throughout this week. We are also offering this course at 9 a.m. again tomorrow morning. So there's an opportunity for your colleagues to sit in on this if you have some people in your organization that could benefit from this type of education. So please feel free to distribute an invitation to anyone in your firm who could use this webinar and take advantage of it. Also, if you haven't signed up for the other two courses, those registrations are still open. So if you go to the original invitation and click those links, you can register for the other two seminars that we're giving this week. One last thing I'd like to touch on before we get going here is just the Buckley and Jeremias partnership. Buckley and Jeremias entered into a partnership a little over a year ago now, and I really can't say enough about these guys and the engineering and technical support that they offer and the resources that are available in the Northeast through Buckley and Jeremias. Larry, who will be presenting today as well as throughout the week on various topics, and his team at Jeremias, I really feel are the best engineering resource on factory built duct and vent systems. They can provide full engineering calcs, 3D drawings, Revit models, and if you were logged in early enough and saw the video, you probably saw that they do industrial chimneys as well. And those are all self-supporting stacks that they do the full structural analysis on and can provide that into projects as well. I'm extremely proud of what Buckley and Jeremias are offering this week. It's an in-depth course on the sizing and application of venting systems and grease duct. Buckley has been in the stacks and breaching business for a long time, and frankly, I really feel that the technical side of the venting industry has been overlooked for quite some time now, and I'm really happy that we're able to offer this to the engineering community in the Northeast here. There are a lot of people on the line today, so if there are questions that come up, please use the chat function. We'll be monitoring that throughout the course, and if questions come up, I'll interrupt Larry, we'll address the question and move on. So again, use that chat feature, we'll be monitoring it. And with that, I'll hand it over to you, Larry, and let you get going.
Thank you, Dean. Thank you very much. Hello, everybody. I'm Larry. I'm going to shut my camera off so I can spend more bandwidth on writing on the screen and so on. Welcome. We do encourage any questions whatsoever, and also obviously encourage Dean. We have Michael Lucia from Jeremias, also he's the Eastern Regional, and also Alex from our Senior Applications Engineering team is on the line with us also. So they will be interrupting me, hopefully off and on with any questions. I do want to give a quick introduction to Jeremias because we know that the name is very strange, it's kind of new, so we want to make sure you know where we come from, where we're going. We'll be spending most of the time on the ANSI venting categorization. This tells us when and what type of gas vents to use. We'll take a look at each gas vent system that is manufactured by Jeremias, get into the NFPA 54. This is the National Fuel Gas Code, and take a look at some common code violations and tables. And then everything that is not covered by the ANSI venting categorization means it's pressure stacks. So we're going to touch base on pressure stacks also. Then we're finished up today right at the introduction of the ASHRAE chimney design equation. This is for the part B of the system. There is a couple of handouts in case you didn't catch when I mentioned this earlier. The handout for today, the NFPA 54 tables, that would be a good one to print out. It's actually 6 pages, so be sure that's downloaded. All you have to do is click on it, double click on it, and it'll be downloaded in your web browser, and then you can print it out. It's a PDF, or just look at it on the screen. But we're going to be spending some time on that. So let's take a look and get started. Again, this is a quick introduction to Jeremias. We go by three strong words. We're strong, we're open, and we're international. So something to think about. We are one of the youngest manufacturers coming out of Europe. We started in Germany back in the 1970s. This is the founder right here. His son, Stefan, is the current CEO of the group. The group consists of 8 manufacturing plants around the world, plus the blue is distribution centers. So we started in Germany back in the 1970s. Now we have manufacturing plants in Spain, UK, Poland, Russia, and the newest operation is here in the States, just north of Atlanta. We're proud about the management here for the past 3 full years. This is the management team. Matt Bertler, the managing director, he was the director of engineering at a company called Duravent. I'm sure you have that in your specs. Clark was the director of engineering at a company called Selkirk. They also have a brand called Amco and Heatfab. Francois was a plant manager at Security Chimneys in Canada. Maxine comes from Jeremias, Germany. So on the line with us, we have Michael Lucia and myself presenting. So that's a little bit about the management team. This is the Jeremias tech team. This is the group of 10 young engineers that's doing all the work. They're doing the CAD calculate, or the CADs, the seismics, the Revit design. So this group is highly trained. We're excited about them. They're all engineers, and again, being very heavily trained with the specifics of venting technology. This is our manufacturing plant located just outside of Atlanta, 75,000 square feet. We've only been producing for about 5 years, and I just realized that we're at 100 employees as of today. So rapidly growing. Inside the plant, something special about Jeremias is that all the machinery, most of the machinery is actually built by Jeremias in Germany for the manufacturing plants around the world. So we brought in all the machinery on the boats. The machinery comes from Jeremias, Germany, but 100% of the products for North America is produced here in Atlanta. So we're proud to be using their machinery, but everything with the materials and the production is all built in the States for the North American market. We have our own R&D facility in Ohio. This is in Logan, Ohio, Southeast. This was, we actually opened this up 8 years ago, several years before we actually started producing, because there's a lot of testing that goes on. The third part of this series, we're actually going to be looking at videos of us actually burning up some systems inside this lab. I know a lot about this facility. I was at this facility back in the 80s, not to date myself. Clark, our director of engineering, he worked in this lab back in the 1990s, 2000s a little bit. So we're very familiar with the lab. This was the old metal asbestos lab from the 1970s that was built. So that was just a quick introduction of Jeremias. We are, European technology. There's we can't hide that. Now we're made in USA 100%. The machines are specifically built by Jeremias. We do have international support. Some of the things we're doing is really new to the North American market with how we create the joints and how the systems are leak-free. And we're growing very rapidly. We do expect to be the new leader in North America in the commercial arena within just a few more short years. Maybe Michael, did I mention anything about the company that I forgot? I mean, I'm doing a quick 2 or 3 minute flyover, just a quick introduction. I won't be talking no more about the Jeremiah's, the company.
Now, Larry, I think you hit all the touch points perfectly.
All right. I do ask Michael to come in just to make sure that I'm not just sitting there talking to myself, the internet's off or something like that. So we're going to start out with the ANSI appliance categorization chart. This is something that was developed in the early 1990s. This was developed because the natural gas appliances started to become more and more efficient. It was quickly realized that with the condensing appliances, type B gas vent, or even pressure stacks was not lasting very long with condensing appliances. So this chart consists of the horizontal axis where everything above is basically non-condensing. The dew point is at least 140 degrees above the dew point for the flue gases. Everything below the horizontal axis is condensing. Efficiency-wise, you could say maybe this is 87% or greater efficient. This was maybe 85% or less efficient. And then from the vertical axis, we have vent pressures. So you have negative vent pressure for categories 1 and 2, and then you have a positive vent pressure for categories 3 and 4. So that's really the 4 criteria that you're concerned about when you have a vent system. Is it negative or positive? Is it condensing or non-condensing? That's where this chart comes into play. So what we're going to look at is a typical appliance that is applied to each one of these categories. It's important to realize that in some cases, a single appliance could be part of multiple categories. It depends on how it's vented to which category it is. The purpose of the categories is to tell us what type of flue to use. So category 1 would be something that has a draft hood on it. Anything that has a draft hood on it automatically is a category 1. It could also be a fan assisted. It could be a fan assisted furnaces are pretty popular still today, at least in the South. Probably everything's condensing up north, but here this is a little small fan that brings in combustion air. You still have a negative vent pressure coming out of the furnace, so that would be category 1. It's not condensing. Category 2 is sort of phased out a little bit because there's no appliance that is specifically listed as category 2. Some of the category 4 appliances, they say when you common vent them, they're category 2. So we'll get into that when we do some common vent sizings with ASHRAE on the second half of this series. Category 3 would be a positive vent pressure, non-condensing. Something like a tankless water heater is a very common category 3 where you're venting outside through the wall. It's the flue gases are positive. It could be maybe a direct vent system where it's a fan assisted, where you're bringing air in to the appliance and you're exhausting out the side wall. Again, there's some appliances that are category 1 if it's vented vertically, or it's category 3 if it's vented out the wall. Then category 4 is when you get into high efficiency condensing appliances, maybe something that uses plastic like PVC or a true condensing boiler. So that's some of the appliances, but the real purpose of having these categories is to tell us what is the vent requirement, what UL requirement is required for the vent. So let's take a look at first category 1. The requirement is a UL 441 standard for type B gas vent. So type B gas vent is only used on category 1. Must be category 1, otherwise you cannot use type B gas vent. So we do have actually all the Jeremiah's models, double wall models are listed to this UL 441. We actually have a type B gas vent, very inexpensive, but our condensing flues as well as the on-one systems also carry that UL 441 label. Category 2 is when we introduce a new standard. This is UL 1738. This is the standard for special gas vents. Myself, I would have called it maybe type C for condensing, but the standard was created called special gas vents. That's UL 1738. That's the requirement for categories 2. All of Jeremiah's models, because we have an all-in-one technology, we have gas vent only, and then we have all-in-one systems. So every one of the systems is rated for category 2. 3 and 4 all use the same UL 1738 standard. So the standard can take positive pressure. The standard can take continuous condensation. So we're good for categories 2, 3, and 4 are the 1738 standard. So now we know a little bit about the categories, what the different categories mean, and then what type of flue is used on each one. A couple of things I want to talk about is our overlapping joints. Every one of the joint systems that Jeremias makes on the gas vent systems and the on-one pressure stacks is overlapping. That's critical to see and note that this is an overlapping joint. So just to kind of review our double wall, this is gas vent, GB stands for gas vent, is good for all categories. The single wall is not good for category 1. A double wall, a type B gas vent has to be double wall, so this is only good for the other categories. And then you have a type B gas vent. We buy the Echo brand out of Canada, which is the type B gas vent for category 1. So just a quick review again, the double wall gas vent's good for all categories because we have the dual listings on that. We have the 441 listing as well as the 1738 for all the double wall systems. And then the single wall is only good for categories 2, 3, and 4, not for category 1. A little bit about the joints we're looking at. This is the gas vent system, the small diameters. It's important to note that how we make the joint is we actually expand the female side. So the one side is expanded, a gasket is added here. So when you install the system, you always have the protection of the inner pipe protecting the gasket. So if the system is properly sloped, the condensate stays away from the gasket. You're always good to go. I like to show this slide also because our small diameters 3 through 12 inch, the single wall UL 1738 product is actually designed to be cut to fit, just like PVC. So you can actually cut this to fit, just like PVC. The contractors can take nothing but 4-foot pipes to the job site with elbows and actually safely install a system easily and quickly. So it is cut to fit because we are competing with PVC. On the larger diameters, we go with an overlapping system that uses a flange. So we actually add a flange to the outside of the pipe. This has caulk applied to the flange. So when the system's installed, it uses a V-band technology, which is very common in the industry. But the nice thing is that you have the overlap, you got the inner pipe protecting the seal, the seam, or the seal, or the silicone seal. So that's what's important about the Jeremias way of doing this. This is one of the reasons we grew so large so quickly in Europe. So all others, this is what we see a lot of. They put the silicone on the flange, you put the system together, you got a slight bridge, slight offset where condensate can lay. There's actually one manufacturer has a 3-year leak-free guarantee. Basically, that means it takes 3 years for the condensate to pass through a 1/2 inch thick silicone because it's just not going to last. So they all will eventually leak, but the overlapping design is the way to go. We do want to take a look at the labels on the different 1738. This is this is out of the instructions here. I do want to point out that we actually have 5 different temperature listings. There's 7 available into the standard. Most other manufacturers have only done the 550, like Heat Fab is a popular one. Some manufacturers like Duravent only do the 480. That's why they're only a 1/2 inch airspace versus the 1 inch airspace that everyone else is. We actually did both of these testings. We actually did the 400 purposely because we know that any condensing appliance typically does not get above 360 degrees. So on our label, we have a 400 degree temperature. And then if we use fiber insulated systems, we actually have a 0 clearance to combustibles going vertical. So it's important to have a 0 clearance to combustibles. We also like to use fiber a lot, just to always have a man-safe skin temperature. And then we did the lower temperatures to follow the plastic applications because we see a lot of people using our stainless steel systems instead of polypropylene or PVC. This is what the actual UL label looks like. This is required by UL, exactly what we can say, but we talk about the special gas vent. This is UL 1738. You have the type B gas vent, that's the 4441. The type L, that's 641, that's good for oil. So all of our gas vents carry all three of these UL listings. The single wall systems gas vent, we actually went with 4 different temperature listings. So we did the 550, the 480. Then we have the polypropylene in the CPVC, PVC applications. Again, we're the only ones that went this far because it's real important that if you're using this stainless steel as a replacement for plastic, you want to make sure you have the same zero clearance to combustibles. It's worth noting that on PP applications, you actually have a 1/4 inch on the horizontal to combustibles if you fully enclose it. So this is what the label looks like for the single wall system. The UL label has the different temperature listings. We don't have type B gas vent listing on this. So this is the single wall, which is only the 1738 listing for special gas vent for the single wall. I do want to comment about the state of Massachusetts. You guys are on the forefront. I think the state has recently outlawed, I guess is the correct name, PVC and CPVC. Michael, I think you talked to Vincent about that a couple weeks ago. Feel free to pipe in and confirm that. So we are seeing that our single wall system is the plastic replacement all around the country. And I want to bring this up because 6-inch diameters are popular commercial diameter for special gas vent or for CPVC, PVC. And look, it's really not that much more expensive than polypropylene or CPVC. So we're seeing a big flow toward the stainless steel arena for special gas vents on condensing appliances. We have available a lot of charts. This is something that was taken out of a plumbing engineer. It talks about the UL 1738 stainless steel and the aspects of it being safety, warranted, listed, designed for positive pressure, none of that with PVC. Installation is fax and easy versus all the priming, cleaning, the versatility of the listings and the categories versus only the appliance being approved for PVC. The warranty, in this case, Jeremiah's 25-year warranty versus no warranty at all. So there is a big national scene going towards stainless steel on plastic approved appliances. A couple things I want to point out. A lot of your specifications that you have is outdated. We want to make sure that you realize that the AL294C has been discontinued. It's no longer required by just about all appliance manufacturers. That has been removed from their IOMs and replaced it with UL 1738 stainless steels. We're seeing that 444 was what Jeremiah has been using since we first came into the States. It's actually being melted in the States for the first time. We use 316L on large diameters. Both of these are UL 1738 approved, and it's not really about the materials, it's about the joint anyhow. So we see a lot of leaking systems with AL294C because they're simply just bad joints. I do want to comment that we do always use stainless steel in the outer jacket, and we always use all stainless steel for all supports and accessories. When you think about the materials of any vent system, think about being 100% maintenance free. And that's what everything we have to show you today is 100% maintenance free. A couple little things. We do have stocking partners around the country. So there's about 6-7 different locations that stock single wall gas vent and then double wall gas vent systems in various diameters. So just a quick review. We do want to just mention again that the double wall systems, every one of the systems we make, both just simply the gas vent as well as the all-in-one systems, are approved for all categories. And then the single wall is only good for categories 2, 3, and 4. The type B gas vent's only for category 1. So just a quick review. We think we have the most complete lineup on the market. We're one of the few manufacturers that go from 3 to 48 inch across the board for 1738 and Type B gas vents. Michael Lucia, anything that I missed on the categories, and a little bit about the flue types?
No, sir, you covered it.
So we're going to spend a little time on NFPA 54. So hopefully everyone had a chance to download the 6 pages that show some of the design rules and some of the tables. Now, we didn't talk too much about NFPA 54, the National Flue Gas Code. We want people to think about we're going to be using ASHRAE, the ASHRAE Chimney design equation, and that's going to be part 2 of this, but we feel that you really need to understand the NFPA 54 because that covers the routing conditions. It covers how you both do common venting and individually vented systems. So the more you know about or understand the National Flue Gas Code, the better you appreciate the ASHRAE system. So the ASHRAE is a steady state calculation which does not account for modulation or stack priming period. So we want to make sure that you know a little bit about the National Flue Gas Code before we start getting into the ASHRAE Chimney design equation. So some of the things we're going to cover, my short 35-year history of traveling around the country, seeing a lot of stack systems and chimney systems, I can assure you I saw a lot of different weird things, but I kind of compiled a list here of some of the most common code violations. And so we have statements out of NFPA 54, which is the National Flue Gas Code. So the first one, the most common one, was that the horizontal manifold was too long. The standard actually talks about the horizontal manifold cannot exceed 75% of the vertical height. So if you have a vertical height of 20 feet, 75% of that is 15 feet. So if you have a 20 feet vertical stack, your horizontal cannot exceed 15 feet. That kind of makes sense because flue gases, they want to what? They want to rise with the natural draft. We'll be looking at that with the ASHRAE Chimney design equation. So what happens is this is a little dark area. This is where you get into trouble because flue gases want to rise. They can't. They're going to condensate, sit there until the stack is entirely primed for the stack to start working. So we want to make sure that you know that 75% is the rule there. You also have a rule that says 1.5 feet per every inch of diameter. So if you take a look at a chart, 10-inch diameter times 1.5 is 15 feet. So if this was a 10-inch diameter flue system, and this is 100 feet tall, you still cannot go more than 15 feet of horizontal. Because again, the flue gases, they want to rise, but you're making them go horizontal. And even the 1/4 inch per foot slope that's in the code doesn't really help that much. So we want to make sure you realize that there's this rule right here. Many times the stack systems are oversized. So there's a 7 times area rule. So the code says that the diameter of the common stack cannot exceed 7 times the area of the smallest flue connected to it. Why is this important? This happens because if only this appliance fired by itself, the small amount of flue gases is not enough to heat up that large oversized stack. A cold stack is not going to draft. The flue gases have to be hot. The chimney has to be primed for it to be able to draft out properly. So this is where this is important. The stack is actually oversized. If you look at a chart, but anything that would be like an 8-inch outlet, if this was an 8-inch diameter outlet, the common stack cannot exceed 22. So if it's a 24-inch diameter, that's not good. The small outlet cannot heat up that 24-inch space. I think we'll be looking at a little bit later on some 12 and 14-inch diameter systems. So we're good to go as long as the stack is under 30 or 36-inch diameter. Oversizing the stack is very common. Now, you can also oversize the stack by the MBH. So there's an input MBH, and we're going to be looking at that shortly. And what I did is I just did some simple reverse engineering, and that calculated to be 200 feet per minute. So anything less than 200 feet per minute means very likely your stack is going to be condensing, even though it wasn't designed to be a condensing stack. Your forced draft boiler, you're going to see condensation. So that we'll be talking more about maybe using insulation between the walls versus airspace and stuff like that. Stuff like that to help minimize. The connector rise, this is critical. We could see something like a 100-foot tall stack with only 10 feet of horizontal. And if you don't have this 2 feet on larger diameter, you're not going to have a flue gases venting properly. They're going to be spilling out the barometric dampers in the draft hood. So the connector rise is a critical part of the system. We think about that even into condensing and forced draft applications. Mixing of multiple appliances, this would maybe be a forced draft boiler with an atmospheric water heater, or maybe fan assisted, or maybe even condensing. You're going to see that the flue gases will come out the forced draft or in priming periods, and they'll make it out to wherever they need to go versus up the stack until the stack is primed. So you want to make sure you're not mixing different kinds of appliances together in the same stack. We see a lot of masonry type of construction out there. We want to make sure you realize that a masonry stack is not a positive pressure capable flue. We see a lot of condensation in these kind of stacks, and we see a lot of stacks failing near the top. So you want to think always about lining these systems. There's a lot of great commercial lining systems out there, easy to install, so that's always an option. And finally, what we see a lot of is that we see these issues out there. Maybe the stack is too large. Maybe the system is oversized. Maybe the connector rise is not working. So what we see is that people are slapping draft inducers in the stack. And then what you have after the draft inducer is an entire pressure system, which may not even be designed for positive pressure. So we want to make sure that instead of a temporary solution, that you have a chimney expert actually take a look and see what the solution would be for long term. So that's just a couple slides there with the common code violations. So we're going to kind of jump right into flue sizing for the gas tables. So we want to make sure, again, there's some handouts that we included on this webinar, and you want to download, preferably print, the NFPA 54 tables. These tables will show us some definitions that I'll go over. So show you some general rules that are often forgotten for both single and common, and that way we can size up some flues. Okay? Dean or Michael, you guys all still with us?
I'm still here, Larry.
All right, sounds good. A little bit about you're good. Okay, so a little bit about the definitions, the height, obviously. And this is great because this will show all the consultants, the engineers, the contractors that's on. You know, we do need the routing information to size up something. So we'll see more of that, and we'll keep on showing this more and more. So it's all about having an experience of what our internal chimney experts are doing as we're sizing these up. But of course, the vertical height is from the flue outlet to the termination. Laterals is the total horizontal vent when you look at the tables. FAN means fan assisted appliance. You got the minimum, the maximum allowed per each diameter. NAT means natural draft or a draft hood. Of course, the maximum amount per the table. And then you got the connector rise. That's the important connector rise that we talked about, being from the vent connection to the bottom of the manifold. There's some general rules. You know, there are 20 pages about all the rules used to size these tables, but I like to maybe show the 2 or 3 that tends to be forgotten. The tables assume there's no more than 2 90-degree turns. So each additional 90-degree turn, you reduce the capacity 10%. Anything less than 45 degrees is considered horizontal. And of course, the horizontal cannot exceed the vertical or laterals as shown on the tables. The tables may show 100 feet vertical, then only maximum of 50 feet horizontal. So if you got a 60 feet horizontal, 100 feet vertical, you can't even size the system. On combined appliances, when you have a manifold, the table assumes there's the common vent is straight vertical. So if I just sketch something here on the right, you have, this is the stack right here. The tables assume that you have boiler 1 and boiler 2 like this. Now, I want to point this out because I hardly ever see a mechanic room that has that capacity. I typically see a mechanic room that has maybe boiler 1 and boiler 2 like this, and then you're routing over to where the shaft is and going vertical. So that is a common manifold. So when this is the case, we have to reduce the tables 10% because there's a manifold present. Furthermore, if there's an offset, maybe below the roof line, you're going slightly horizontal before you offsetting below the roof and going vertical, that's an offset. You got to reduce the tables another 20%. So in a system like what I just sketched over here, you'd be actually reducing the tables a total of 30%. Of course, we mentioned the horizontal not being too long, 1.5 times the diameter, or the common stack cannot be too large. And also make sure you take a look back at the common vent not being below the minimum capacity at any given time. So we're going to take a look. And again, the purpose of going through these tables, even though they might be outdated, I know there's not too many fan-assisted appliances out there, but the purpose of us going through this is to make us better chimney designers when you're using the chimney design equation. We're giving you access to a computer calculation, an HTML format, so we want you to be able to use it, but we want to make sure that you have some kind of experience on using these tables first. So we're going to start out by looking at a very small system. It could be an atmospheric water heater. This may be something like you have at your house. 50,000 BTU with a 4-inch outlet. I'll open up the tables. So this is what hopefully you have on your second monitor, or maybe you have printed out. We're going to take a look at a 50,000 BTU. So the system is 10 feet of vertical. You have 2 foot of horizontal. It's a 4-inch outlet at 50,000 BTU with a natural draft appliance. Capacity is 81,000. 4-inch diameter is perfect. We just sized the first stack system. So we're at a 4-inch diameter. Oops, get back up. We're at a 4-inch diameter here. Second system, we have the same heater, now 6 feet of vertical, 4 feet of horizontal, and 5 elbows. So we're looking at the same table, 6 feet of vertical, 4 feet of lateral. I go over to 4-inch diameter. I have 64,000 MBH or 64,000 BTU capacity, but we have 5 elbows. We have to take 30% off that. So 64 times 0.7 is 44.8. That's not going to work. Jump up to the next diameter, 103. 103 times 0.7, I'm at 72,000 capacity. This vent system needs to be a 5-inch. We need to increase from 4 to 5 at the outlet. So now we're at a system here, which is 5-inch diameter, just because of the routing change. That's perfectly fine. I mean, the 5-inch flue on this 6 feet of vertical, 4 feet of horizontal, all these elbows will be perfectly fine. Next system, let's look at maybe more of a commercial 1.4 million BTU fan assisted appliance with a 12-inch outlet. The vent routing is 15 feet of vertical, 2 feet of horizontal. Let's open up, oops. Let's open up the same table. We'll go to the bottom where it's continued on. We have a vent system that is 15 feet of vertical, a 2-foot offset. This is a fan. So we start at the 12-inch flue. The maximum BTU is 1495. So we're perfectly fine with the 12-inch diameter flue, which is the same as the outlet. So now we're at a 12-inch diameter here for the tables. And the last one we'll take a look at is the same heater, now with only 10 feet of vertical, 5 feet of horizontal, some extra elbows in there. So we look at the bottom side of the table. We're going to see that we have a routing of 10 feet of vertical, 5 feet of horizontal at a 12-inch diameter. We're at 1.2, we're already below it, so we'll go up to a 14-inch. We're at 1596, but we need to reduce that by 20%. That means we're at 1276. We need to be at 1400. We need to jump all the way up to 16-inch. So use 2238 times 0.8, 1790. So we're actually going to use a 16-inch diameter. Go from 12 to 16. We're allowed to increase 2 sizes. So it's 1, 2. So we need a 16-inch diameter on that last system. So a good reference to kind of maybe think about how important the routing is when we think about diameters and pressures. So that's the table 1. The second table is a common vent table. So this gets a little bit more complicated. We look at using another set of tables. So this is 3 1.2 million BTU 12-inch outlets. I think that's the same size that we looked for. So 1.2s, 12-inch outlet, and we're basically going to determine what all these diameters are here. Okay, so we start out. The first thing we think about, we do a check. Does the horizontal exceed 75% of the vertical? So we're at 20 feet of vertical. We're only at 10 feet of horizontal, so we can proceed. We're okay. If the horizontal exceeded the vertical, we would say back to the engineer, think about using dedicated stacks. Well, think about using the draft inducer. We try not to use anything mechanical in our stack systems, but sometimes you just can't help it. We would maybe do an engineered system with fiber insulated stacks or something like that. Make sure the connector rise was even higher than normal. There's a lot of things you can look at. Is there a manifold before the vertical? So this is a manifold system right here. So what we need to do is to be sure that we reduce the common vent tables 10%. Is there an offset in the common manifold? There's an offset in the common stack. So now we need to reduce the common vent tables a further 20%. So now we're reducing the common vent tables by 30%. So the first step, how we do it, is typically size the connectors. So I'm going to get into the second table. So we're looking at a system that is 20 feet total rise. The connector rise is 3 feet, so we always want to use the least on the table. So we have a 2-foot connector rise. We know this is fan maximum, so we start out with a 12 inches the outlet. We don't have that 1.2 there. We need to jump up to a 14 inch. So we basically have a 14 inch. We need to go from 12 to 14 inch right away on these connectors. So we got to close this. So the answer is we're basically using a 14 inch diameter. Very common, you have to increase the connectors when you manifold the appliances together, when you look at the National Fuel Gas Code tables. And that's something we kind of learn when we start using the ASHRAE chimney design equation when we size forced draft appliances and condensing appliances, because sometimes it's better to increase the connector diameters than to oversize the common stack. So it is okay to increase the connector size up to 2 sizes. Second step is to size the common of the 2 appliances. So in this case here, we have the bottom table, which is the common bent diameter table. We have a total rise of 20 feet. In this case, we have 1.2 or 1200 MVH times 2, so 2400. It's all fan plus fan. So when we think about 2400, appears like 16 inch will be okay, but we need to reduce that by 30%. So 2722 times 0.7 is 1905. They need to be above 24, so jump up to 18 inch. 3561 times 0.7, that's 2492. 18 inch is the requirement for the 2 appliances. The 18-inch diameter is the requirement there. The last step in the sizing is to size the common for everything. So let's get back into the tables again. Now we're looking at a 36-inch diameter system. So we have a 20-foot vertical rise. Look at the fan plus fan, 27 needs to be at least 36. Here's a 4548 times 0.7. That's 3186. We need to go up to 5573 times 0.7, 39. So we're looking at all fan assisted appliances, a 22-inch common stack. So we just sized up the complete system. However, we got to do some more check. Is the stack oversized? So the outlets is 12-inch diameter. Remember back at that chart I mentioned, the 7 times area, a 12-inch could actually go into anything, not anything larger than 30-inch diameter. So we're okay at the 22-inch diameter. Does it exceed the minimum input rating? Well, let's go back and look at these tables. We have the minimum allowed input rating. So on a 20-foot tall stack with a 2-foot connector rise on a 22-inch diameter, what's the minimum allowed? It's actually not applicable. This is telling us that you cannot have a 2-foot connector rise. You must have at least a 4-foot connector rise. So we would have to actually go back and say, look, you need to raise this header up another 2 feet. You must have at least a 4-foot connector rise, and you cannot fire these at half fire. Otherwise, you can get into a condensing type situation where you're not supposed to be condensing. So again, the purpose of this is to start getting and thinking about the routing of the system, the critical areas of each, the connector and the common, because we're actually be looking at this on the next similar portion as we get into the ASHRAE equation. So just a quick review, we did cover a lot here. So what happens if the appliance is not categorized? And if it's not category 1, 2, 3, or 4, that's when we say we call it non-categorized. Some people call it forced draft. This means typically the burners can be removed and replaced with maybe another type of burner, maybe another type of fuel. So these could range from natural gas to oil, a combination of both. But this is where we move into a new UL standard, UL 103. So UL 103 means it's basically a 1,000 degree chimney system. These are always stainless steel of some kind. Typically 316, I think, should be used. If not 316, or 444 is actually better than 316. Some of these, most of these actually go up to 1,400 degrees. Most of these have a pressure listing. By the way, Jeremiah has 90 inches after 1,400. Everyone else on the market has 60 after 1,000 because they don't have that overlapping design that protects the silicone seal. So the building heated appliance chimney, the UL 103, again, this is what's used for everything that's not categorized. UL 103 could be maybe a Scotch Marine, could be maybe something out of factory heating equipment, maybe an oven or something like that. So this is where you get into the building heated appliance chimney. We do want to show you the products that we use. We use a Conical System. I know Conical spelled with a K in German, so we get the same KL as they do in Europe. So we also make an FL for Flange. So we're excited to kind of show you these two products. First of all, 444 is the standard stainless we use. We use 444 because we buy a whole melt at a time. That's 90,000 tons of product that we buy at the same time. And so 444 is always used on the inside, which is good for condensing, non-condensing. We always use fiber insulation. We actually use the fiber to hold the inside and outer pipe together. And then we always use a 3 or 4 stainless outer jacket and the high pressure joints. So I do want to show you a little detail of this conical system. We do this on small diameters. We actually started at 36-inch diameter, and now we only do it on smaller diameters because it's easy to install in small diameters. But we form this conical shape, and all you do is you push the product together and you tap it in place. So this is a push fit system that actually has a 3 psi, 90 inches of water column of pressure rating after 1,400 degrees. So this is good for special gas vent. Jeremiah invented this conical system back in the 1970s, and today this is what everyone does in Europe for a pressure stack that uses conical system. And then on the double wall, what's unique about the conical system is that you don't have there's no brackets and stuff used to hold the inner and outer pipe together. We use nothing but insulation, which is shoved between the walls, and you're done. And so because of that, you have zero clearance to combustibles. You always have man-safe skin temperatures on high temperature applications. Even above the roof, see how the system is expanded so it flashes down. This is 100% silicone sealant, maintenance free because of the technology. And it's actually very easy to make. Then on larger diameters, up to 4 foot, we go with a flange system, but we put an expansion on the one side and add the flanges to the outside. That way, when you make the seal, install the system, this is very similar to our gas vent. You have this inner pipe protecting the seal. That's great for grease duct applications and high temperatures. Unlike we talked about, everybody else has that offsetting type of construction on the flange to flange. So just a quick review. We have the UL 103 pressure stacks. We do the flange system on large diameters. We call it the FL. We have the conical system, KL systems. The entire system is stainless steel, maintenance free. 16 different UL listings on these two product lines. This is good for condensing, non-condensing. It's good for grease duct, pressure stacks, engine exhaust systems. So it's very unique that because we're using that 444 stainless steel inner, you always have the good type of steel. So we're wrapping up. This is something that everyone should probably make a note of right here. There's a website link here. www.usdraftco.net/appliance.aspx. I'll just go to this link real quick. This is what is given to you as a handout on the next one. As I go to this link, this is what you will get is this HTML program. So this is what we'll be using on the second part of this, is that you actually input the appliance. And this, what you're seeing on the screen, is the replacement of a 27-page equation found in the ASHRAE Chimney handbook, or the ASHRAE equipment handbook. So this is what we'll be looking at next, the next session. You actually input the horizontal distances, the vertical height. You can actually calculate what the theoretical draft is going to be. You actually calculate what the pressure losses are and how them two work together. So this is what we're looking at next time. And just to kind of give you an idea, it's all about the flue pressures at the outlet on just about any appliance. So we start out by looking at, I call this my slinky stack slide, where you can actually take and go from 5 feet to 50 foot tall and see all the various pressures that you can get from looking at the ASHRAE chimney design equation. So that's what we'll be covering next. I saved about 4 or 5 minutes for any questions at all. Dean, anything you want to add before we close out the first session?
Yeah, sure. Thanks, Larry. And as I look at the chat right now, I don't see any questions that have popped up. But a few things that I'll just say, that second session that Larry's talking about, that's being offered tomorrow at noon and 3 p.m., as well as Thursday at 9 a.m. So if you haven't signed up for that yet, and you want to dive deeper into how these systems are sized and actually go through the calculation process and look at the tools that we have available, then I would highly recommend signing up for that session. If there's anyone within your organization that hasn't signed up for this yet that you think could take advantage of this opportunity and this education, please forward it to them and encourage them to sign up. As I said at the beginning, registration is still open for all of these courses. And thank you for joining us today, and hopefully we'll see you on the next one. And thanks, Larry.
Thank you, Dean. We're signing off now. Thank you all. Stay safe. Hope to see you on the next